Now that we have standardized our variables, we can actually formulate our Bayesian model. So already copied some code in here. So as before, so we have with pm model s, so we create a context for the pymc3 model. I will call the model normal because I'm going to assume that mortality, treatable mortality in this case, so we're modeling mortality, that it's normally distributed. And the reason is that mortality is a sum variable. It counts the number of people who died per 100,000 inhabitants. But the fact that it's a sum variable means that it's going to be normally distributed. Yeah, because sum variables tend to be, so the variables based on sums tend to be normally distributed. So first we need to give the priors on our coefficients. So we have a constant. So again, remember that we type constant here and then repeat the same name here in quotes, constant. So the variable constant, which is the constant of our regression equation, we're assuming that it's normally distributed with mu equal to 0 and a standard deviation equal to 1. Yeah, so basically the idea here is that all our variables are standardized. So if a country has average values for all the explanatory variables that we're going to use, like GDP, inequality, etc., its value for mortality is going to be based on the constant only, because if a country has the mean value of GDP is standardized, so it means that the value of the standardized GDP is 0. So then all the variation will come from the constant, and because our variables are normalized, it's not unreasonable to work with a constant which then has a mu equal to 0 and the standard deviation equal to 1. The next thing is that each of our priors, so for the coefficient on GDP, inequality, etc., they all have this standard deviation prior, and that standard deviation sigma prior is actually set at quite a small value, equal to 0.1. Yeah, so that basically means that one standard deviation shift in GDP, yeah, because GDP is a normalized variable, so if I shift it by 1, that means that I'm shifting it by 1 standard deviation, will have an effect of 0.1 standard deviation on mortality. Yeah, so that seems relatively small, and the reason why we're choosing it small is because we don't want the models to start overfitting. Yeah, so we're sort of giving tight priors around 0. Yeah, so for each of these variables, the mu is going to be equal to 0. So it will take quite a bit of evidence before our coefficients B on GDP, inequality, smoking, etc. are going to be moved away from 0. Yeah, because the prior is quite tight. So it's going to be hard to get it away from 0. So in that sense, it looks a bit like a ridge regression where you have a penalty on the coefficient that moves away from 0. In a Bayesian analysis, we can do the same by simply giving a very tight prior. And sometimes, because it's used to avoid overfitting, these are called seatbelt priors. So basically priors that you set in order to be safe, and in this case safe from overfitting. So we set these priors for GDP, inequalities, smoking, how much people smoke. I think this is the fraction of people smoking more than 20 cigarettes a day, if I remember correctly. Whether somebody has a high body mass index, binge drinking, and a variable on the dummy, whether somebody is female or not, because we already noticed that female mortality tended to be lower than mortality for males. And we also noticed that there was an interaction here with GDP, so we'll also have a prior for normal B female GDP, and here also we specify mu equals to 0, standard deviation equal to sigma prior. So remember that if you're doing this in the in a Jupyter notebook, in order to get the Greek letter for sigma, you type sigma as if it was LaTeX, and then you press the tab key. Yeah, so if in a Jupyter notebook you want to get the Greek letter for sigma, you type sigma as if you're typing LaTeX, and then you press tab, and that will turn it into a Greek symbol for sigma. Yeah, so these are all our priors on the coefficients. So now we're going to formulate our model. So first so basically what we're going to say is that mortality is going to be normally distributed. Yeah, again, because it's a sum variable, so it's reasonable to assume that it's normally distributed. So repeat the name, mortality. And it's going to be normally distributed with a mean of mu and standard deviation equal to sigma. We still have to specify those, but this is just to see how we're going to build up the model, where observed is going to be equal to our variable log mortality. Yeah, so now I have to specify what mu and sigma are going to be. So mu is going to be our constant. Yeah, so we're specifying here our regression equation. Then there is this dummy for gender. Yeah, so we're going to have this effect B female for when it's the mortality of women that we're modeling. So we have the B for GDP times GDP, the B for inequality times our variable inequality, plus the B for smoking, times our variable smoking, plus the B for high BMI times the variable high body mass index, plus the B for binge drinking times our variable binge drinking. And then we get the interaction effect B female GDP times GDP times gender. Yeah, so this is our mu. And then our sigma so recall sigma cannot be normally distributed. So actually I'm doing this wrong here, so I should start like this. So it's going to be half normal. Because sigma is positive and normally distributed values can in principle be negative. So we specify a half normal here. We repeat again the name of the variable sigma. And we specify here the half normal parameter equal to 1. So then we have mortality, already done that. And we're going to say trace normal is pm.sample. And let's say we want to sample 2000 samples. And we can also tell the algorithm that we want to tune it with 1000 samples. Yes, so it's going to use the first 1000 samples to tune the algorithm. So let's see whether we didn't make any mistakes here or any typos. No, that seems to be working fine. So now it's doing the sampling. That all looks okay. So then we can refer back to the model. We can say with normal. Yeah, so remember that's the name of our model, with normal. We also want to have the predictions equals pm sample this is the one we want, pm sample posterior predictive from trace normal. And for the prediction, the variable name we're interested in is mortality. So let's see whether this works. So whether you have errors here. No, that seems to be working as well. So we can continue. And then we say that the data posterior normal is going to be from pymc3 trace normal, and posterior predictive is going to be the variable that we just defined, ppc normal. And then we can run this as well. Yep, okay, so this doesn't give any results. So here we have formulated our model. We sampled from it. That's happening on this line here. Now we do the sampling. The sampling went quite quick, so then we got posterior predictive. So we can make these plots again where we can compare the predictions of our models, so the 95% prediction interval of our model with the data that we actually have. And finally, we made sure that the information on the trace of the model, so basically the posterior distribution of our parameters, and the posterior predictive are in this object called data posterior normal, so that we can refer to it easily later on.